So we are going to basically use xv6 for our purpose of investigating into the kernel code. So xv6 is actually Unix-like operating system. So it is a port of old Unix version which was implemented for some old architecture, some PDP 11 or something like that, but that has been ported by some MIT researchers to some to modern architectures. So it comes in two variants. One is in Intel x86 architecture, and another one is a RISC-V architecture. So most of our systems are using x86 architecture, so we are going to use this version only. So in the lab, the version that we have asked you to download and install is this particular version, xv6, which is ported for implementation on x86 architecture. I hope everybody has installed that. Did anybody face any problem? Okay. So to run this xv6, we don't have a spare system where we can basically going to reboot it every time and change anything. So we are going to use an emulator for this purpose. So we will basically run it with QEMU, which is called quick emulator. So it is an emulator which emulates the underlying hardware, in this case the x86 architecture, and the underlying in the make file you can specify how many CPUs you want. Generally it supports multi-core architecture, so you can specify the configuration, and according to that it will emulate that particular architecture, hardware architecture, and over that this xv6 kernel will run. So we will see xv6 in action using this kind of an emulator. Okay, and why we are choosing this? Why we are not choosing a real OS? So has anybody idea how many lines of codes will be there in a real OS? Any estimate? It can go to millions of codes, and it will be too overwhelming to navigate through that code, what to speak of understanding it. Okay, how many of you have written long programs? Anybody written thousands of lines of code?
Yes.
Okay, so at least you have some experience of writing at least a long code, all in a single file or multiple files? Multiple files. So what it was in assignment given in DSPD. Okay, so at least you have some exposure to writing multi-file programs, but still you won't have an exposure to a very large code base. So this will be probably your first exposure to a large code base like an OS. But this xv6 is actually mainly done for teaching purpose. So it is mainly used by teachers and students for understanding the underlying operating system concepts, how they are implemented. So they have made it very concise and compact. So probably something, I think 6,000 lines of codes are there. So they have tried to include as many functionalities as possible, and the code is mostly in C and assembly language. The code is written mostly in C and assembly language. So you will see .c and .s file in the code base. We will see soon that. And it generally we can see we can divide into two categories of codes. So mainly we have two categories of codes, or broadly still not comfortable with the pen. Two category of code. One will be kernel programs, another will be user programs. So the code can be broadly divided into kernel programs, which contains all the kernel implementations, and the other will be user level programs, which are available for users for writing their programs and testing and all that. And you know, user programs cannot directly call or any kernel code, so they have to call through system calls. So there will be system calls or definitions that will be written, and we will see that today in this particular class. That okay. And in user programs it includes some basic user functionalities, user library. Does not include C, so we are not going to use C library. We are going to use just whatever is provided by xv6. So some very basic string manipulations and some very basic utility programs and functions for that, and that is all we will have to work with. So it will be a little bit different than your normal experience. Okay, so let me just with this introduction, let me start exploring the code with you. So I have downloaded that folder and installed this. So in this, if you see the files, so these are the total number of files which are there in the xv6 folder that you download. So I have not made it, I have not compiled it right now. So it only includes C and H and S files, assembly files. So no object files and so on. And to understand what these files are there is a good thing about this. There is a well documented PDF files, PDF code manual which is available. There is a book and there is a manual available. So the links are there. I'll share. I think we will share that soon. So this is, I think, a manual of the code. And if you see in the first page itself, it basically lists all the various files which are there in the xv6 folder. So you can see the first category of files are basic header files. And these are mainly these includes basic definitions of functions and constants and all that you define that basically kernel is going to use. So this is mainly for kernel code. And then the next category of files you can see is basically code which is used to enter into the xv6 code. So whenever so xv6 is just like another a program that you may have written, and mainly the entry point is your main function, isn't it? But this is not a normal program, it is an OS. So before it executes and before it actually starts main, it has to set up some things in the hardware, and that setting up thing is actually done in this entry.assembly file. We will see that later on. Right now, so with that now, right now logs and all that we will discuss later on. Process we have started, but again we'll come to process later on when we discuss other things. So these are process related files, virtual memory, process, Kellogg, and switching, context switching. So these are codes which implement all those things. So these are going to basically these are the files which include all the mechanism of allowing user programs to run as process and enable multitasking and multi-programming and all that. Okay. But coming to the system calls, that is going to be today's focus. So for system calls, there are these many files to enable the functionality of system calls, there are these many files which are there, and today we'll try to at least take a glimpse of some of these files, how system calls are implemented. And then there are file system related files again that we will discuss when we come to file systems and so on. Maybe one category you can see user level programs, programs related files. So you can see there are some files. There is a usage.assembler file. There is a init.c file, because init is the first program which when OS boots up, the kernel boots up, init is the first process which is launched, and it keeps running till OS runs. So that is the first program, and then init calls, in turn calls this shell program, and that shell program is where you are going to type your commands and execute your commands. So these are the codes for that. Okay, I think that is enough for this thing, and let me now. So so how to compile this code? Basically, there is a make file there. Again, make file is very complicated make file that you may not be able to understand everything. So there is a make file which defines all the rules. There are so many files here and how they are all there. So this make file contains all the rules for compiling not only the various files, but also how to emulate the QEMU related the hardware architecture. So it has all this details for QEMU and all that. So right now let us not worry about make file, but just let us use it. So if we run make, it will going to basically go through an involved compilation process, and it takes some time. If you have not done it even once you have done it even once, then only it is very quick. So there was no error, so it has compiled successfully. Now to launch it, we have to use QEMU. So we can use make QEMU to launch it, but right now I'm using WSL on Windows, so I don't have a graphical interface, so I have to provide a no X option here. No X is no X forwarding, so it is mainly to disable graphical thing. So I cannot run graphical thing. So if I try to do it here, it won't allow it. It will give some error. So I have to give an option and Nox QEMU -Nox, and then I can basically do it. So as you can see, after compilation, it is basically now started the emulation. So in the make file, I think there are two CPUs defined. The number of CPUs were defined 2, so it has emulated 2. You can make it 1 if you don't want multi-core. So you can see there are 2 CPUs it has emulated, and then there are some statistics about your file systems. So we'll discuss that later on. So if I do ls, so this is a shell command, shell program. Init has started shell, so now it can receive commands. So I have just used a basic ls command. So you can see this. These are the mostly user level programs which are there in this xv6 kernel. So you can use any of these commands to basically do. For example, you can use grep. Grep command is used to search some patterns in the file. Make dir, let us say CSL 309. Okay. Yeah, so yes, it has created a directory. So it's working. Most of the commands will be working anyhow. So that is not. So now let us see if you have to add a user program. You want to add a user program in this list. So how do we do that? I have already added a hello program. So just to save time, I have written hello.c here. So you can see user.h is a file which includes all the functionalities which are available for user programs to use. So all the system call definitions and as well as the user library functions which are available, they are basically written here. I hope this font is okay, or should I need to increase? Okay, I think that should be sufficient. So there are user programs here, and how much time I have? Okay. So these are the user.h. You can see what all functions you can use in a user program. So we are not going to use any other thing. A simple printf function we are going to basically use. So I need to include user.h and types.h basically if you have to call system call and all that. And I've written a main function, and I'm just want to print. So this printf is not a C printf library function. So it's slightly different. We have a first one argument here which basically specifies where you want to printf, whether it is a standard out and all that. So one represents your standard out. So I've just passed that. Standard out here will be your terminal and a statement. Okay. And instead of return, we cannot return here. We have to exit. So xv6 does not allow return. So if you have to, after main, we have to do an exit system call. So it's a simple function. So we can write this hello.c in the same folder, xv6 folder. And we need to now, in the make file, we need to add this thing. So where we add, in the user programs variable, we append one thing here. So these are the user programs. We just appended similar. We have to follow the same process. So underscore hello is the file that we have added. So underscore hello slash, and I think there is another variable extra. So in this also we have to append hello.c. So once we do this, then we have basically once we do make, your hello will be compiled, and that's why we have already, because it was already done, hello is available. So we can run the hello program. So this user program that you have just now added, or at least I have added it, so it is running and it is executing a hello printf statement to the console. So it's a very simple to add any user program is very simple. Write a .c file, save it in the same folder, and in the make file, in the extra and user program variable, you just append your new file name that you have added. Okay, and then make clean, and again do the compilation using the make file. So you will be able to add any user programs that you want to add. So for testing, you will have to add a user program to test your whatever changes that you have done, you need to add. Okay, now if you have to add a system call, then you have to now change your kernel space. So how to do that? How to make changes into your kernel space? So the kernel space. So in the book of xv6 book, if you go to page number 9, there are details of the system calls which are already implemented. So these are the system calls which are already provided in xv6, and which are some standard basic system calls that you need for process creation and all that, file reading, writing, and so on. Okay, these are the system calls which are already there, and it looks they are generally the same as which are as they are in the Unix or Linux operating system. Okay. So now if we have to add a system call here, what we can do first, we can take a look of any of these system call in this file, in this code base. So let us say we take a look at getPID, how this call is implemented. So if we go to our code base, so let me quit the so let me remove the object files, otherwise there will be too many files. Okay, so right now we have only code files. So let us say I want to find getPID wherever this getPID is there in all the files. So it has written me, it has searched all these files and shown all the instances where this get PID pattern was found. Okay, so there are 7 to 8 files in this code base. So I think these 2 files are just testing this get PID function, so we can neglect that. Apart from this, there are 6 locations or 6 files where this get PID system call thing is something related to this get PID system call is implemented. So that is syscall.c, syscall.h, sysproc.c, and usys.s. So let us look look into this one by one. So first we'll look at syscall.h. So as we have said that every system call will be identified by some system call number. Okay, so you can see that number has been defined in syscall.h. There are these were the system calls which were there already. So if you have to add a system call, we will basically define a number to that particular system call. So using the same pattern sys hello, we can just take the next available number 22 and append it. So that is one thing that you need to do. Then if you go to sysproc.c, you see this function contains all the implementations of system calls which are related to process things. So see, get PID was basically implemented here. So this is a basic implementation of this get PID. It is basically returning the PID from the myproc structure. So we'll have to also implement our new system call in a similar way. And if you see, all the headers of all the system calls are same. If you see, the headers are all the system calls are same, irrespective of whether they may take an argument or not. For example, system kill takes an argument. If you see, kill actually takes a PID, because it has to know which process it has to kill through PID. But here the definition does not has that argument. Here that is void. So that is for a reason. So all of them returns an integer value, which is basically used to define whether it was successful or error happened or something. So if it was successful, some positive value will be returned. If there was an error, some, I think, 0 or negative value will be returned, and so on. Okay, and arguments for system calls are not passed through this way. For we'll see that any argument for system calls, if it has to pass, it has to be pushed into the stack. So we don't explicitly pass through a function call. So that's why there is a void for all system calls. The implementation takes only void. It doesn't take a system call. So we need to retrieve arguments from the stack. So there are functions, utility functions meant for that. Argint is a utility functions. Later on we can see that. So here we don't need anything. So we have added a syscall, and again we are not doing something useful. I am just printing a statement. So because we are printing into from the kernel code, so I have used a console printf statement function, not the regular printf function. Normally it's not a good idea to do a printf into the kernel, but just for explanation we are doing it like that. Okay, so here we have implemented our system call. So this is the implementation of the system call. Okay, so that we do in sysproc.c, and then we go to syscall.c and see here what is happening here. So here what we are doing, basically we are defining basically an array, a table, a syscall table, which is basically nothing but an array of function pointers. It may not be so intuitive to C programmers, but you know there is something called function pointers, na?
Yes.
So this is what it is. But it is just defining an array of function pointers, and we have to, for each system call has been defined a function. The function pointer has been defined at a particular index, and that index is the number, the system call number that we have defined. So this syshello is the particular 22 number. So at 22 index we will have this syshello function pointer. And this is a neat trick we will understand later on. This is a neat trick to implement this so that OS does not has to have a separate thing for each system call. We'll talk about that later on. And then also we define a prototype for that function and add extern here because the implementation is in some other file. So we indicate that this is an external file which has to be linked up while compiling it here. Okay. So that we need to do here. So every system call that you have to add, you have to follow this bureaucratic process that you have to follow this pattern. Okay. So we will come to this why this kind of table is there later on. And then this is an important thing to understand. Okay. So this is assembly code. What we are doing here, we are defining a macro basically. So this is a way to define a system call in user space. So in syscall, sysproc, we have basically defined the system call related information in the kernel space. Now to make it available to the user space, we need to basically do it through this. And how user calls a system call, remember system call is just like another function call when we are going to use in our user program, but it is a slightly different than a function call because it encapsulates a trap instruction. Okay, so that thing is being done here if you see, and normally you cannot encapsulate a trap instruction directly in a C file. So we are using an assembly language code here. So this is a macro which defines a assembly level function. And what it is basically doing, it is defining a name. So we are basically wrapping a system call function. We have added our system call hello. Okay. So it basically, whenever that particular system call is called, it basically jumps to this label name, that corresponding label name. Okay. And when it jumps to that name, it does two main things. So what it is doing, one thing, it is moving a value to EAX register, and another thing, it is calling an int instruction. Int instruction in x86 architecture is an interrupt instruction. So it's slightly confusing. It's not an int data type. Int here is actually a interrupt instruction. Okay, and that interrupt instruction is being called by a particular value. So what basically this macro is going to do, it is going to basically so for example for your hello function, it is going to define, when you compile it, it is going to create this assembly code in your code base. So it will create a hello label. And whenever that hello system call is being called by user space, it will jump to here, and then it will execute two instructions. First instruction, it is going to move a particular value, which was your t_syscall number. So for hello, we have defined some particular number. Remember, we used the number 22. So that particular number is going to basically get loaded into EX register. So EX register is a general purpose register for in x86 architecture, so that you can use it. Is a accumulator register basically used for many purposes. So we use EX register here to know which particular system call. The OS needs to identify which system call it has to code, it has to run, and that it will know by reading from the EX register. It will get this value 22, and then it will go to transfer the control to that particular code base. So that's why we have to first basically store this number, and then basically it has to issue a trap instruction. So for all trap or all interrupt, there is only x86 points only one instruction called interrupt, but you have to specify a particular number. Through that, it will know whether it is a trap instruction or which kind of interrupt. So here, because in x86 all system calls related traps are given a particular number 64. So that number will be replaced here basically. So we'll see this number where this number is coded. So this is going to basically this t underscore syscall is defined. Basically you can see in traps.h, I think this will be defined. T underscore syscall has been defined a particular number 64. So that number will be replaced, and sys underscore name, it will take the name from here, and we have defined sys underscore hello with particular name a value. That number value 22 will be stored into the EX register. Okay, so that's how it does. So now how the OS knows from 22 how it will jump to that particular function. So that is what that is why that particular, so it takes 22 number, and now it looks into this system call table, and from that system call table it gets that function pointer syshello, and that syshello is then invoked by the OS. The control gets transferred to that particular system call for implementation. So instead of basically doing it for each system call separately, this is basically a trick that that this is being used here. So for you, if you have to add a system call, you don't need to do anything more now. You don't have to do. You just have to add uses the macro name, and then you are done basically. After that, you can add. Also, you need to add in user.h because you need to make it available into the user programs. So you need to add the prototype of that system call in user.h, and then you can use that function that system call safely in your user program. So now you can use this system call hello that you have just now written, and compile it again, for example. I think I had done make clean, so it had removed all the, so it is again going through the entire compilation process. Otherwise it would have just compiled the hello.c file which was changed. So now if I run this hello program, you can see now this system call, the work of the system call is also done, which the hello from kernel statement that we have inserted into the kernel space, that has also been executed. So in your lab, basically we will ask you to add a system call and test it. So you need to go through this process. You need to add a user program for testing that and add a system call, and you need to basically follow this bureaucratic process of doing a modification in every of this system call, and then you will be able to add a system call. Now I think we don't have much more time to left. So I think you have seen some things of how system call is implemented, but some more things are not, some more technical details are there. What I will do is I'll pass you the reference where you can read all that. So how the other functionalities, how the OS basically prepares the hardware to basically, so if you remember in the main function, if you see the entry function, after that it basically initializes trap vectors. It calls a function trap vector initialization. So this trap vector initialization, basically what it does, it calls some, it prepares this interrupt descriptor table that we have discussed in the class, which basically tells at which code basically which interrupt has to, for particular interrupt, which particular code has to be there. And this of course you will not be able to understand, but so if you see this, that was a macro. So this offset is that particular address where it has to jump. So that offset address is being provided here. So in this, you see we are providing that t underscore system call address port for that particular interrupt. So I think you may not understand everything, but just glimpsing through it, and you if you remember, whenever a trap instruction is handled, the hardware has to store the context of the user program. And to store that context, there is a trap frame is being defined here. Okay, so it is going to store all the general purpose register values and so on. So it is going to basically, so we are storing, we are providing that in the trap frame, and some other things like EIP is the instruction pointer register, the PC program counter, and so on, and other things are there. So okay, so hardware pushes all these things, and then rest of the things are, I think, has to be pushed by the OS code. So this trap frame, where it is being basically, so when this will be called, basically when 64, when that particular interrupt is going to be invoked, it is going to jump to a function all traps, and this all traps function basically is defined in this. If you see this all trap function, it is going to build this trap frame. It is going to push all the values onto the stack, kernel stack, and when that, and then it will basically call the trap function to do the to handle the system call, and after it has done, it will do a return from trap. So all that thing is being shown here. So I know that this all will be going above the head, so I don't want to now, but those who are interested, they can basically, I will give you the links to understand these things in more detail. So I think I will stop here. I hope it has given you at least a glimpse into the xv6 code, and see that whatever we discuss in the lecture, something similar has been done here in the actual code thing.